Hi everyone, I'm Yi-Hsuan from National Cheng Kung University, Taiwan. I'm presenting a lightweight curved surface system composed of bending active plate units, a study of materials and composition. The bending active units were formed by inserting a brace into precast slits on a sheet and forcing outer plane deformation that kept it bent in a self-stabilized state. In formal research, an empirical function of approximate estimation of the bend angle was proposed. A catenary arch and a geodesic dome made of 3 mm plywood units were presented in IASS 2019. In this paper, different unit connecting patterns were studied, various kinds of materials were tested, finite element analysis were performed and compared with the measured results, and full-size structures were built using different materials to verify the size effect. Finally, a modified composition was developed. First, we measured strengths at different locations of the bending active units to study the deformation behavior. The relationship between actual strength and the seat depth ratio showed that all the actual strength increased as the seat depth ratio increased, and the relationships were linear. The value of the negative strengths were always larger than those of the positive strengths at the same locations. This indicates that the major areas were subjected to not only bending but also to axial compression. 4 types of analytical models were used to simulate the active bending deformation using SEP 2000 and ANSYS. The comparison between the major strengths and the analytical model shows that all 4 models can simulate the linear relationships between strength and slit depth ratio. The ANSYS solid element model had the least error and the performance of the frame models was the worst. However, only the shear model successfully demonstrated the actual compression suggested by the major results. Several types of material were tested with 3-point bending to determine the material most suitable for the full-size structure. We define the bending capacity as a ratio of fracture strength to elastic modulus, and the material efficiency as a ratio of elastic modulus to material density. The test results show that GFRP plates had the highest bending capacity and the lowest material efficiency, while aluminum shows the lowest bending capacity and the highest material efficiency. The laminated bamboo tend to fracture at the groove interfaces and thus were considered unsuitable for the proposed system. Finally, 3 mm thick plywood and GFRP plates were chosen for the subsequent construction. We studied a new composition with carbon models, the ITL system, where units were connected by interlocking the braces and the neighbor units to create a staggered pattern that avoids the alignment of the flexible areas and resulting in a weak link. The carbon models work well, however, attempts to build a full-size circular arch with 2 mm GFRP plates were not successful. The scale effect might be the reason. We changed the design to pointed arches to reduce the bending moments. Plywood plates and GFRP plates were used to build a full-size pointed arch. However, the GFRP pointed arch could not maintain stability, while the plywood pointed arch stood stably on the self-weight. However, visible deformation was observed. It stood for 11 days and then collapsed due to a lateral wind load. Microstructural analysis using SEP 2000 was conducted to study the difference between the plywood and GFRP arches. Geometrical nonlinearity due to pure data effect and large displacement were included. However, neither of the analytical models for the plywood or GFRP exhibited instability and the deformation was severely underestimated. Another micro-finite element analysis that superposed the internal forces caused by self-weight on the bend units were conducted. The analysis for the GFRP micro-unit model was unable to converge, but the same error did not occur in the micro-analysis for the plywood unit model. Because of the failure of the previous system, we proposed a modified system, the OL system, where the units were overlapped and bolted to the neighbor units. It enabled a direct path for internal forces and improved the stability. However, the bend angle was changed in the new system, so the old equations were not applicable. We had to study the new bend angles, like shown in the right. By using the modified composition, we successfully built the final four-size structure. Here you can see these are all the materials used and how the units were assembled. Here are how the prefabricated parts were assembled and lifted up to form the complete structure. The final four-size structure weighed only 28 kilograms. After being built, only slight deformation was observed. It was assembled in 10 hours and stood on the outdoor side for more than 5 months. This concludes my presentation. Thank you for your attention.